Hello, everyone. Welcome to our first lecture for the Sensation and Perception class. Today, we're going to be exploring the question, what is perception? So, go ahead and grab your coffee or tea, get comfortable, and we're going to spend the next hour and a half chatting and exploring this fascinating question. So, what is my goal for this semester? This semester, we will, of course, study and discuss new information, memorize terminology, facts, theories, brain structures, and neuronal pathways. That said, my true aim for this semester is to encourage critical thought, to facilitate fluency in the language of psychology and neuroscience, and to apply that knowledge to help us understand old questions and old answers, reframe current questions and answers, and to ask questions that we've never thought of. Each of you in this present moment hold the potential for the future within you. Whether you choose to pursue opportunities in psychology or neuroscience, the practice of acquiring new knowledge and applying it to novel situations is a skill that you can call upon in both your personal and professional life. While sensation can seem rather straightforward, here's the sensory modality, touch for instance. Here are the receptors associated with the modality, and here are neuronal pathways connected to those sensory receptors. Each sensory modality is intricately connected and interwoven with neural pathways for other senses and neural information, resulting in our greatly varied and subjective experience and perception of reality. The interaction of these lower level sensory experiences with higher level perceptive, cognitive, and mentalizing processes help us to understand some of what is happening on the microscopic level in the context of atypical mental states, as well as states of mental distress, such as attention difficulties and emotion dysregulation. The assertion that humans only have 5 senses dates back as far as the work of Aristotle, in which the 5 senses were associated with 5 elements: sight with fire, hearing with the upper air, smell with the lower air, taste with water, and touch with the earth. In addition to processing more than 5 senses, humans possess a highly nuanced experience of each individual sense. Consider touch for a moment. Take a few seconds to think about the different kinds of touch that you experience. Touch alone is greatly varied. We experience the sensation of itch, pain, warmth, heat, cold, light touch, pressure, and vibration. These varying sensations of touch are mediated by different types of sensory receptors in the skin of different shapes, sizes, and depths that allow us to experience the nuances of just touch. A few of y'all might be sitting there scrolling through Instagram thinking, okay, fine, Miss Davis, we get it. Sensation is a lot more varied and complicated than the basic 5 senses we were taught. But why does it matter? Sensation is much more complicated than, for example, the simple experience of a stimuli touching the skin, activating the sensory neuron, traveling from the primary to secondary neurons until the signal reaches the cortex. So this is an upper level psychology class. So think about the mental perception of sensation. A really simple example is pain. Have you ever wondered why, when we feel pain, we experience an emotional response? I mean, after all, it's just another sensation on the skin. What makes it different? The sensory neurons involved in the perception of pain actually travel along a neuronal pathway that reaches the anterior cingulate gyrus and amygdala, brain regions that both display activity during experiences of pain, both physical and emotional. As we broaden our understanding of what other interactions with internal and external stimuli might be considered senses, let's consider what the purpose of human sensory ability might be. Why do humans need to be able to see their surrounding environment? What is the benefit of being able to taste? What advantage, if any, does being able to hear afford humans? And what about pain? Why on earth would pain be helpful? Consider each of these senses from the evolutionary perspective. Highly attuned senses dramatically increase one's ability to identify potential threats via a variety of mediums. You can see wild animals prowling in the distance. You can hear the thunderous rumbling of a stampede headed in the direction of your encampment. You might even smell the scent of burning trees, hinting at a fire and cueing potential danger. When foraging for food, bitterness might signal that a food is poisonous. Brightly colored animals similarly might aid indication of creatures with poisonous mucus coatings. Not only did our sensory abilities facilitate our survival and evolution, but our multisensory ability was truly an advantage. Imagine if you lost one of your sensory abilities. It might prove to be an annoyance or a challenge, but you would still be able to navigate the world. However, imagine that you only have one sense, just one, vision, with which to help you understand the landscape of your external world, to help you steer clear of danger and head towards food sources and safe areas for rest. If you only had one sense, and you lost that sense, your ability to simply live life, not to speak of surviving threat, would be greatly challenged. Being multisensory humans confers us with an incredible set of tools for survival, adaptation, and artistic experience of the world around us. After all, what is music without the ability to hear the notes and feel their vibrations? The setting and rising sun without our eyes to gaze upon it in wonder and awe. The senses are incredibly powerful tools that allow us to understand our external environment and shape a coherent perception of reality that allows us to navigate the world with safety and, dare I speculate, opportunities for joy. When framing sensory abilities as an evolutionary benefit that facilitates survival and adaptation, consider hunger and thirst. Might they also be considered senses? From one perspective, hunger and thirst can be understood as the experience of internal chemical signals communicated to the brain, resulting in a physical sensation that communicates to the individual that they are hungry or thirsty. This may be considered a response to internal stimuli that provides information about an internal state. And I think that an app just visualized the notification in this recording. So I'm going to pause this recording, turn off those notifications, and then start this again. Pardon the interruption. Let's dive back in. Okay, so from one perspective, hunger and thirst can be understood as the experience of internal chemical signals communicated to the brain, resulting in a physical sensation that communicates to the individual that they're hungry or thirsty. This may be considered a response to internal stimuli that provides information about an internal state, prompting the human to seek water and food to nourish the body. From another perspective, such as Candel's, he argues that the term sensory should, strictly speaking, be applied only to afferent inputs that lead to perception. Consider the sense of vision, hearing, taste, touch, smell, and proprioception. They all have designated sensory neurons that respond to stimuli for the relevant sense. Taste buds help us taste foods. Rods and cones are photoreceptors that help us see. Merkel cells, Meissner's corpuscles, Pacinian corpuscles, Ruffini endings are all cutaneous touch receptors that facilitate various types of touch. Some research indicates that sensation of internal states such as thirst may be mediated by osmoreceptors located in the hypothalamus. These osmoreceptors are sensory receptors that detect the concentration of certain hormones in the blood, and under certain conditions can trigger the hypothalamus to induce a thirst response. While sensation and perception are sometimes colloquially used interchangeably, they actually refer to two distinct processes. Sensation refers to the process in which physical external information, such as light, sound waves, food, or an object, is converted into neural sensory information that the body can interpret. Think of it like pressing a button on the keyboard. The button press is the external stimuli, the sound wave. When you press the button, an internal mechanism in the keyboard is activated, receives that signal, and if the button press was hard enough, it initiates a response. And just like if you don't press the keyboard button hard enough, you won't see a letter on your computer screen. If the external sound wave or touch isn't significant enough, it won't stimulate the sensory neuron enough to start the signaling process. The process of pressing the button and sending the signal is akin to the process of sensation. The perception refers to the process that occurs when the brain receives that sensory information, processing it, and determines what to do with it, what it means. Returning to this keyboard metaphor, pressing the button activates an internal mechanism that initiates code, leading the computer to generate a letter on your computer screen. Similarly, when your brain receives the information that your hand has come into contact with your coffee mug, it processes that sensory information and then generates the perception of touch. Simply put, sensation is about stimuli and perception is about interpretation of stimuli. Various models exist for explaining the process of sensation and perception. The standard model of perception asserts that sensation begins in the sensory organs and proceeds via bottom-up processing. Bottom-up processing can be conceptualized as a data-driven process in which information from the external environment interacts with sensory organs, such as photoreceptors in the eyes or cutaneous receptors in the hands, and activates a unidirectional process from the sensory organ along the sensory neural pathway to increasingly higher order cortical regions. Each successive stop along the path towards the cortex integrates the visual information, eventually leading to an interpretation of the meaning of the value of that sensory information, culminating in perception. Consider this image of the Russian dolls resting on a table and think about the variety of visual information that the photoreceptors need to integrate. What strikes you first? While you think about that, I'm going to have some tea. Well, there is more than one doll. How can one distinguish that there are different dolls? Well, the dolls are different sizes, The highlights and shadows from the light illuminate each doll a little differently. Each doll has multiple colors painted on them and slightly different designs. Although the objects have human-like faces painted on them, they're not just tiny humans. We don't see them as tiny humans, crazy as that may sound. We see them as dolls. The photoreceptors in the eye capture this great variety of sensory information: size, shape, color, light versus dark, texture, and allow us to perceive the varied components of images like this. But how does this turn into the perception of the actual dolls on the table? As the information passes from the photoreceptors in the eyes to the thalamic nucleus to the visual cortex and the occipital lobe, the integrated sensory information passes to higher level cortical areas that allow the brain to interpret visual components such as motion, form, color, and spatial location. Each sense relies on specialized neural cells to transduce physical stimuli into an electrochemical signal, a neural response, in the form of an action potential. Even greater variety exists within the sensory receptors associated with a particular sense. Consider the photoreceptors. As you may recall, the rods and cones in the retina serve different functions. The rods are sensitive to light and dark, whereas cones are best adapted for well-lit areas and allow us to see color. For gustation, while there aren't necessarily distinct types of taste buds, each individual taste buds are selectively responsive to certain types of soluble chemical stimuli, or tastes. Interestingly, our taste buds actually regenerate every 10 days or so. Handy. Our sensory receptors of the inner ear, necessary for hearing, are also pretty fascinating. Once sound waves travel into the ear canal and vibrate the eardrum, the tympanum, the vibrations travel further inward to the inner ear ossicles. There, the sound is conducted through the cochlea and guided towards the hair cells. Particular sound frequencies, low versus high, for example. Hold on just a moment, I lost my place in my notes. Right. Particular sound frequencies, low versus high, for example, stimulate certain subsets of hair cells, allowing humans to not only differentiate between different sound frequencies, but also to spatially localize sounds. For instance, low frequency sounds will reach each hair cell of each ear at different times. This is called the interaural time difference. We'll get into the details of this later, which helps with spatial localization. As high frequency sounds travel a bit faster, it will be more difficult to discern the differences based on timing. However, the high frequency sound hits the hair cells closest to the sounds and then passes the head to reach the hair cells in the opposite ear. By the time the sound reaches the opposite ear, it is softer, again, facilitating our ability to spatially localize sounds. Unfortunately, while taste buds regenerate every 10 days or so, hair cells do not. So be careful with your hearing. Once damaged, you're unlikely to naturally regenerate new hair cells to recover the lost hearing. Throughout the semester, we'll study the nuances of these receptor cells, the types of sensations they're sensitive to, their morphology, the neural pathways along which their signals transverse, and how this massive array of sensory information is masterfully transformed into perception. Further complicating this process of sensation and perception is the concept of phenomenology, our subjective internal experience of the world that we perceive. Reflect back on the last time you heard your favorite song. How did you feel? Did you feel excited and energized? Did it make you want to dance, run, or play? Or perhaps it was a soulful song that inspired you to pull out your guitar or get on the keys. Did you tap your feet, smile, laugh, furrow your eyebrows in intensity as you experienced the journey of the music? Or consider the last time you watched a sunrise, a sunset. What did you feel? Listening to a song or gazing upon an expansive vista are deeply sensory experiences. Some might say that music is nothing more than sound waves traveling through the air, vibrating the eardrum, stimulating our hair cells to fire an action potential. But the experience of listening to classical music, R&B, soca, or jazz is so much more than just the firing of neurons and passing of action potentials. This takes us from sensation into the throes of perception. Almost as if by magic, the myriad photons that activate our rods and cones cause neurons to fire. And as those action potentials pass through the optic nerve, one of the 12 cranial nerves, from the retina through the thalamus to the visual cortex, the visual information is processed and translates that light and dark, color hue, depth, size, and shape information until it forms a coherent visual that we perceive as the ocean, the mountains, the sunset. And still, our human sensory and perception experience extends even beyond this to the experience of the phenomenon, the feeling that accompanies hearing your favorite song, the evening sunset, your morning cup of coffee. Just as much as this phenomenological experience can confer on us feelings of joy, the experience of beauty and awe, we can experience disgust and revulsion. There is nothing quite like experiencing the pungent aroma of garbage along New York City's sidewalks on a humid summer afternoon. So much of our sensory experience just seems to happen naturally. So it's understandable that we might take our properly functioning senses for granted, as well as the knowledge of distinct sensory systems. I'm gonna need more tea. Biologist Johann Mueller actually pioneered the idea that specific neurons activate a particular type of sensory experience via his doctrine of specific nerve energies. This is the idea that activation of photoreceptors, for instance, will lead to a visual experience, and that activation of the hair cells in the ear will prompt an auditory experience. This knowledge may seem intuitive now. However, in the 1800s, questions such as these remained mysteries, uncertainties. Not only that, given the similar electrical activity observed in neurons at the time, there was skepticism that sensory processes occurred in distinct pathways. And consider for a minute the marvel of the specificity and consistency of our sensory systems. Just about every time you grab your cup of coffee or tea, you feel the sensation of your hands gripping the cup. You feel its warmth if you're having hot coffee, and the cold and the condensation of your drinking iced coffee or tea. Now imagine if every time you grabbed your cup of coffee, you instead saw an apple. That'd be both nonsensical and alarming. Aware of our current findings at the time, Mueller wondered how the brain was able to discern sight from sound from touch, especially if all explored neurons displayed similar electrical activity. Hermann von Helmholtz, a student of Mueller's, continued this legacy of sensory research, and in addition to developing landmark physics theories, he developed the trichromatic theory of color vision, which asserts that color vision is based upon human perception of three colors: red, green, and blue. Although Helmholtz was not certain if this perception of three distinct colors derived from unique cells sensitive to those spectrums of light, future research indeed revealed that cones, the color-sensing photoreceptors, indeed have three subtypes: short, medium, and long, indicating the spectrum of light to which they're sensitive. Helmholtz extended his sensory research to the theoretical realm via the constructivist approach and hypothesized that basic sensation alone was not sufficient to explain the intricacy and variability of perception, nor sufficient to explain phenomenological experience. Helmholtz alluded to the process of transforming sensory information into perception via the concept of unconscious inference. The unconscious inference concept suggests that the information captured by the human sensory system needs to be integrated into our existing knowledge and perception of the world. He argues that via the process of unconscious inference, our brains integrate the sensory information of the world with pre-existing knowledge about those stimuli, those patterns, and what they've represented in the past to guess, to predict what one is seeing in the present moment. Consider the waterfall illusion. If you stare at a dot superimposed on a graphic of a waterfall in motion for about 20 seconds, and you can access this illusion through the chapter. And they look at through the chapter student section link that's included on the syllabus. So if you consider the waterfall illusion and you stare at a dot superimposed on a graphic of a waterfall in motion for about 20 seconds, and then look at a still image of that waterfall, you'll perceive motion even though none is present. The unconscious inference suggests that the brain incorporates sensory information into a larger, complex, inferential system, if you will, that combines moment-to-moment sensory information with previously acquired information to predict what is currently being seen, heard, felt, tasted, or smelled. Helmholtz's work foreshadowed cognitive models, including information processing and the computational approach. Helmholtz, however, was not the only individual trailblazing and proposing theories to explain human sensation and perception. Ewald had his own perspective about the science underlying color vision and perception. He disagreed with Helmholtz's trichromatic theory of color vision and asserted that rather than three distinct color-sensitive cells, cells were sensitive to pairs of colors. And I'm going to pause for a second and plug my computer in before it runs out of power. So, Hering theorizes that photoreceptors are sensitive to pairs of colors. For example, cells were either sensitive to green-red or blue-yellow. He also disagreed with Helmholtz's concept of unconscious inference, instead arguing that the sensory information integrated from the external world was sufficient to facilitate perception, and no internal processing was required. Hering's perspective on perception influenced Gestalt psychology and direct perception theory, while Helmholtz's perception theory is more accepted among experimental psychologists and physiologists. The field of research exploring visual processing is ever expanding and providing further clarification about the nuances of rod and cone activation that facilitate both achromatic and color vision. A 2016 study conducted by Sabizan et al. Revealed that continual stimulation of a single cone led to the perception of white, while stimulation of multiple cones was required to generate perception of color. This was a landmark study, as it was the first time that scientists were able to target, stimulate, and activate single cone photoreceptors of a known spectral type with light. This research also provides evidence that some of the core tenets and theories proposed by scientists and thinkers, such as Helmholtz and Hering, remain accepted to this day. This study relied upon the assumption that 3 types of cones are differentially activated depending on the spectrum of light, alluding to Helmholtz's trichromatic theory of color vision, which still remains relevant for retinal processing. Additionally, this 2016 article asserts that some of the neurons in the retina actually exhibit activation patterns that suggest spectral opponency or color opponency in the retina itself, not just in the visual cortex. While Helmholtz and Hering explore the process of sensation and perception from a more physiological perspective, scientists like Ernst Heinrich Weber, interested in these same processes and phenomena, approach them from a more psychological perspective. Weber's work was popularized in particular due to his explorations of perception, especially as explained in Weber's law. Weber discovered an interesting pattern in perception: the just noticeable difference. Weber explored the ability of humans to sense the difference between 2 stimuli of the same type, but of different magnitudes. Look at the 2 pairs of lines on this slide. Consider example 1, this one right here. Which line is longer? The one on the left or the one on the right? If you said the line on the right, congratulations, you've got highly attuned perceptive abilities. As it turns out, both lines on the right side of the slide, are the longer lines. Not only that, both lines are longer by the same amount. So why is it easier to discern which line is longer in example 2, but it's more difficult to discern which line is longer in example 1? Weber would attribute this difference in our ability to perceive the longer line in example 1 as compared to example 2 as the just noticeable difference. As you experienced, our ability to identify a line that's a 1/4 inch longer is related to the magnitude of both stimuli. It's easier to discern the difference between 2 stimuli of smaller magnitude, as in example 2, than of larger magnitude or strength. Gustav Fechner, who actually named the just noticeable difference Weber's law, is known as the father of psychophysics, a credit for which work explored the relationship between changes in physical stimuli and human perception of those changes. Consider hearing, and that sound is measured in decibels. 20 decibels is actually 100 times louder than 10 decibels. However, psychological studies have shown that humans only experience 20 decibels as double the loudness of 10 decibels. This difference in human perception of the intensity of physical stimulus, Fechner discovered, can actually be modeled logarithmically, such that the rate of perception of stimulus intensity is lower than the actual intensity of the stimulus. Both Weber and Fechner's work explored the patterns in perception of differences in the magnitude and strength of physical stimuli. Weber explored the conditions under which a human could reliably discern differences between stimuli augmented or decreased by a constant amount, as we saw with the line example. Fechner, who similarly explored differential perceptions of magnitude and strength of stimuli, focused on the relationship between the actual change in the magnitude or strength of the physical stimulus and the perceived change in the magnitude or strength of the physical stimulus. So that examples of the decibels. If we increase the volume from 10 decibels to 20 decibels, while the actual difference is 100 times greater, we only perceive it as 2 times greater. Gestalt psychology, while still deeply grounded in exploration of human perception, explored a different facet. Gestalt psychology argued that humans view the world in groupings, patterns, organized structures, rather than individual separable elements. Consider the leftmost image. What do you see? I'll make an educated guess and assume that you're able to see the shape of the letter A. Now look more closely at the individual units comprising this image to create the A pattern. What do they look like? When you focus on each individual unit, do you still perceive the letter A? No. When you look at this image, you don't see a series of randomly arranged X's. And when you look at each individual X, you don't see the larger pattern, the A shape. However, when you view the image as a whole, on first glance, you notice the A shape. To Gestalt thinkers, this ability, tendency to see patterns, is characteristic of human perception. Gestaltists argue that we automatically perceive in patterns, groupings, rather than in individual separable units. Now consider the rightmost image, the Kinshasa triangle. How many triangles do you see? And what color are they? It appears that there is one triangle in the background, outlined in blue, and there appears to be a bright tan triangle in the foreground with little Pac-Mans flanking each corner of this bright tan triangle. Right? Take a closer look at the image. Our minds have perceived two triangles superimposed on top of each other, but there actually isn't a single completely drawn triangle in this image. The triangle that we perceive in the blue outline is actually just a suggestion of one, provoked by the edges drawn in blue, or the perception of edges created by the Pac-Man for the tan triangle. Similarly, the tan triangle is perceptually suggested by the Pac-Man shapes, flanking the corners of the perceived tan triangle. As shown by these examples, in addition to believing that humans perceive in patterns and groupings, they also explored how edges and the illusion of edges, as with the Pac-Man shapes, influenced human perception. In these examples, the edges of the blue-lined triangle and the tan triangle caused us to perceive distinct patterns. The blue triangle, the tan triangle, and the two superimposed on top of each other. Neuroscientific research has been conducted to explore how retinal ganglion cells, the neurons in the retina that aid in visual perception, respond to light stimulation. Hubel and Wiesel explored the reactivity of cortical neurons in the visual cortex of cats. In their experiments with anesthetized cats, they presented the cats with varying stimuli in light and dark conditions and weren't able to elicit a neuronal response from the cortical neurons being measured. They stumbled upon cortical activity when they presented the cat with a slide with a single black dot on it. As they slid the glass slide onto the projector and into the cat's line of sight, the cortical neuron fired. They realized that it was not the black dot on the slide that caused the cat's neuron to fire, but rather the faint line created by the shadow of the glass slide itself. The research alluded to the sensitivity of certain visual cortex neurons to certain types of light-dark stimulation. Direct your attention to the black and yellow concentric circles. Each one has a center region and a surrounding region. There's a center region and the surrounding region. Here's the center region, the black dot, and the surrounding region, the yellow circle surrounding it. These diagrams map out sensitive regions of certain retinal ganglion cells, nerve cells in the retina. Hubel and Wiesel's work has been since extended through research of these retinal ganglion center surround cells, because they have a center light sensitive area and a surrounding sensitive area. Depending on the type of center surround cell, the cell will either have a light sensitive center or a light sensitive surrounding area. For example, center on, surround off cells have a light sensitive center. So center on means sensitive. So center on is a light sensitive center and surround off is a light insensitive surrounding area. In these center surround cells, light stimulation of just the center of the cell will elicit increased firing of the neuron, while light activation of the black off surround will elicit reduced firing of the neuron. Consider the image in the middle of the young girl. The left side of the image was the actual presented stimulus. The image on the right is the computer simulation of the neural response of the on-center off-surround cells, as well as the off-center on-surround cells, to seeing this image. The white areas of the picture, here, slightly along this edge, the white area of this picture signals a strong response by the on-center cells. And the black areas, see the dark lines here, these dark edges. The black areas represent a larger response by the off-center cells. The gray tones represent no response. Notice how this computer simulation seems to emphasize the edges of the image. This is a visualization of the receptive fields of these center surround cells and how they emphasize the edges of visual information. So, why on earth do we care about those center surround cells? Research has shown that these center surround retinal ganglion cells seem to be specifically responsive to the edges of visual stimulus. This activity may have a role in the tendency of the brain to perceive edges, such as in patterns like the Kaneza triangle. Gestalt psychology continued to produce meaningful laws or theories of perception, continuing the theme of the human perceptual tendency to see visual stimuli as patterns and groupings rather than individual separate units. Consider the chart in the middle, showing several of the Gestalt laws. The law of proximity, law of similarity, the law of good continuation, the law of closure, and the law of common fate. Let's look at the image above the law of proximity rule. How would you describe this image? Did you say or think something akin to a series of columns? The key here is that humans tend to perceive this pattern as a series of columns rather than a series of rows. Gestaltist theory argues that this is due to the proximity of the circles to each other. When viewed as columns, the circles are in closer proximity to each other. Whereas if you see the image as a series of rows, the space between each circle would be larger than the space between each circle in the column. So this space is larger than this space, and since this space is shorter, we associate these circles as a group and these as a group, leading to the perception of columns rather than rows. This highlights the perceptual tendency to group items in close proximity to one another, the law of proximity. Consider the image directly above the law of similarity. When you look at this image, did you see columns or rows first? If you saw columns first, congrats. If you saw rows first, congrats. You've just lent additional validity to the Gestaltian tenet that humans tend to perceptually link similar items together. So Gestalt psychology argues that humans perceive sensory information in patterns rather than discrete separate units, and this is evidenced by the law of proximity and the law of similarity, as well as the law of good continuation. The images accompanying the law of good continuation illustrate humans' perceptual tendency to continue the pattern that it has already identified, and to discern objects as separate based upon difference in their patterns. In these images, we perceive the curved line as one image, and this mountain range shaped line, this crooked line, as a separate image. The image below the law of good continuation paragraph, this one here, presents a very different conceptualization of the same image. If the image had not been presented in this manner, in this unique way, would you have perceived it on your own? Okay, let's move on to the law of closure. What image do you see here? Did you think or say a partial circle or something relating to a circle? Completely understandable perception. Now, why didn't you perceive that as a curved line? Kind of interesting, isn't it? The law highlights the human perceptual tendency to complete or close the pattern it sees. This is a near complete circle, and so our brain chooses to complete the existing pattern that it sees, and thus this would create a circle rather than a curved line. And last but not least, the law of common fate. This law involves human perceptual tendencies as it relates to motion. Think about a time that you have watched the traffic along the highway. Have you ever noticed how the cars driving in opposite directions on either side of the street seem to form a group? The cars are traveling at different paces, have different shapes and sizes, and reflect light in different manners. Yet we perceptually tend to group these cars by the common factor: their distinct movement in a particular direction. Similarly, in the example shown here, if dots 1, 3, and 5 were to shift upwards slightly, and dots 2, 4, and 6 were to shift downwards slightly, we'd perceive that change as the movement of two distinct groups. The law of common fate. The previous scientists and thinkers we've discussed thus far have had German roots. The founders of the ecological approach to perception, known as direct perception, were the American husband and wife team J.J. and Eleanor Gibson. This approach presents a direct challenge to the Hermann Helmholtz concept of unconscious inference. If you recall, Helmholtz argued that sensory information alone is not sufficient to explain our perceptual experience, and that unconscious cognitive inference was required to translate sensory information into an educated guess about the world before us, leading to perception. For Helmholtz, perception was like an educated guess, a prediction. For the Gibsons, perception was the complete opposite. They believed in direct perception, that the physical stimuli in the world contained a both complex and abundant source of stimuli, and that there was no need for the brain to reason out, interpret, and make an educated guess about the sensory information received. They asserted that the brain directly perceived the physical stimuli of the external world. They also emphasized the importance of using naturalistic stimuli, stimuli that an individual might actually encounter in the real world, rather than a point of light, simple shapes, or images taken out of context. For this reason, their emphasis on the use of naturalistic stimuli, direct perception, is also referred to as the ecological approach. The Gibsons also introduced the concept of optic flow, which is the perception of motion of objects caused by the relative motion between the observer and the scene they're viewing. Consider driving down the street in a car. As you drive along the street, you see a house far off in the distance, and as you get closer and closer to the house, your perception of its size increases. The lighting and shading changes. Its proximity to you changes. The texture visualized changes. This experience of successively getting closer and closer to the house in front of you and simultaneously further and further away from the stimuli behind you at the starting point presents an individual with continuous visual updates, continually updating visual and sensory information about the proximity between the individual and the objects in their surroundings. Optic flow provides the individual with crucial information about their direction and speed, in particular in relation to the space they occupy, conferring distinct benefits for navigating physical space, avoiding obstacles, navigating towards targets, and avoiding threats. Consider the two images above. Recall the visual experience of riding in a car, bus, or train, looking out the window and watching the scenery whiz by in a blur. The visual blurring depicted in the photos here represents the concept of visual flow. The visual experience of seeing the surrounding scenery also appear to move in relation to the viewer provides the individual with visual information that suggests movement. Herring's work and his opposition to the concept of unconscious inference, an idea developed by Helmholtz, underpins the work of those who pursued the direct perception schools of thought. Just as the work of Herring captivated thinkers and scientists who expanded upon his theories, Helmholtz and his theory of unconscious inference gains followers and further credibility over the years. In the mid-20th century, following the creation of the first electronic computers, scientists began to revisit Helmholtz's theory of unconscious inference, which had previously been quite unpopular. The increase in computing power opens up additional opportunities for artificial intelligence and presented the opportunity to try to duplicate human vision. While humans' experience of vision can be effortless, it belies the neuronal complexity underlying that phenomenon of ease. Scientists quickly came to respect the unseen complexities of human vision as they met challenges in working to duplicate human vision in machines. These attempts revealed the difficulty of training a machine to recognize even a single object, let alone distinguish between many objects in a single scene. Scientists came to realize that it was particularly difficult to distinguish between the edges of objects and to discern the edges of one object from another overlapping object, and to correctly attribute those edges to the proper object. Imagine an apple sitting in front of a box, as you see here. While we can easily perceive an apple in front of a box, a machine might collect these visual data points and have difficulty discerning whether or not there's more than one object. And if so, does the curved edge belong to the apple or the box? Perhaps perception was a bit more complicated than the brain gathering all of this sensory information in response to external physical stimuli and directly perceiving the external world. Perhaps the brain had a role in processing, interpreting, integrating this sensory information. And if we're not aware of those processes, perhaps all of that cognitive work is happening unconsciously. Cue the resurgence of Helmholtz's theory of unconscious inference. These complexities lent further credence to Helmholtz's theory, and unpacking these unconscious processes underlies the information processing and computational approaches to perception. The information processing approach asserts that perception and cognitive processes can be modeled as patterned flow of information from one stage of processing to the next stage of processing. Consider this information system's flow chart. Here, sensory information is passed into a perceptual subsystem where visual data is processed and integrated, and a construct generated, after which that data flows into the cognitive subsystems, where it is integrated with sensory information from other modalities, such as the auditory system, and both the short and long-term memory systems. It's not helpful if you perceive an image and then instantly forget it because you don't have a record of that information stored somewhere. In this model, after visual information is integrated with the auditory sensory information, and no doubt data from other sensory modalities as well, along with the memory systems, the data is fed into the motor systems. Not only is it important for visual information to be integrated with memory systems so that you can remember, whether for a short or long time, what you've just seen, it's also crucial that you're able to physically mount a response to the external stimuli as necessary. Say you're crossing the street, and just before it's too late, you notice a car barreling towards you from your blind spot. You're going to count on that visual information being quickly and efficiently integrated into your motor system so that you can jump out of the way to safety. One of the assumptions of the information processing model that each successive stage is that each successive stage has a finite processing time confers a particular experimental benefit. I'll say that one more time. One of the assumptions of the information processing model, that each successive stage has a finite processing time, confers a particular experimental benefit. If each of these stages is completed within a finite time frame, then with the right equipment and experimental design, perception can be measured. This information processing should not be conflated to a unidirectional flow of information, either top-down or bottom-up. As you'll see, once we begin to explore the neuronal pathways underlying these incredible processes, the brain and body exist in a continual state of information intake, processing, response at such a great volume and rate that it seems unlikely at this stage that information processing is simply a matter of data flowing from point A to B to C. Myriad interconnections between neurons and neuronal systems, as well as connections that excite certain action as well as inhibit other action, might make this tidy information processing model exceptionally complex and alludes to the concept of parallel processing. As information flows from the external environment into the brain processes information and sends signals back to the periphery. The information processing model is similar to the Gestalt view in that both posit an internal perception process that confers perceptive value to the sensory information received. From the perspective of information processing, perceptive value is attributed to sensory information through an ordered system comprised of stages of processing, whereas in the Gestalt view, sensory information is perceived in patterns, suggesting the existence of an internal processing mechanism that translated disjointed sensory information into pattern perception. As with the Knieza triangle, or the A pattern, where we perceived a bright triangle, and although one wasn't actually drawn. The computational approach extends the stepwise approach of the information processing model and zooms in a little bit further to explore what computations, what neuronal interactions are necessary to generate perception. Heavily influenced by the inertia of the emerging electronic computer and artificial intelligence age, as you can infer from the name, the computational approach emphasized a calculated and mathematical approach to unraveling the mysteries of perception. Marr was particularly interested in vision and described vision as an information processing task with 3 levels of analysis: the computational level, the algorithmic level, and the implementation physical level. The computational level emphasizes the what and why of the system being explored. It then uses this information to inform the type of computation necessary, the type of input and output desired to achieve the goal. In the case of vision, the computational level requires study and testing of the signaling patterns and relationships between individual neurons, as well as groups of neurons. The what? The computational approach asserts that these relationships can be mathematically modeled. But why would we want to mathematically model visual input? This could be an incredibly useful tool for those working to program artificial intelligence to be able to see. That is, to be exposed to visual cues, have a system for absorbing that visual information, have a mathematical model for how to translate shapes, shadows, sizes, depth, color, edges, and overlapping objects into code, data that the machine can interpret via an algorithm to complete a task, such as picking up an item. although I don't imagine the robot would drink the tea. So the computational level addresses what the task is and why it's being done. Here, the what can be data-based, create a mathematical representation of a piece of visual information, or it can be abstract, capture visual information. Similarly, the why can be focused or abstract. A mathematical representation of visual information will allow it to be integrated into the larger computational model, or more abstractly, we want the robot to be able to see so that it can mount a physical response to its external environment. The algorithmic level is a set of rules governing how the input fed into the system interrelates and the representations and strategies it employs to feed in, organize, manipulate, integrate the representation of visual data. From a neural perspective, this alludes to the different types of connections neurons have with each other. Some connections are inhibitory, reducing the likelihood of a certain type of response. Others are excitatory, increasing the likelihood of a response. Each of those excitatory or inhibitory responses can also be mediated via connections with other neurons that provide additional information. For example, cone photoreceptors in the retina allow humans to see color, while the rods allow us to see more achromatic, low light situations. The cones will form a combination of inhibitory and excitatory connections with other cones, and the rods will do the same. Despite these rods and cones being distinct types of photoreceptors with distinct functions for vision, they do share synaptic connections. So at the algorithmic level, the information processing task might seek to develop mathematical models for rod interactions and cone interactions, as well as models for synaptic connections between the rods and cones. At the implementation level, the physical structures used to implement the previous two levels. At the biological level, this would be the eyes, neuronal circuits, the neurons within those circuits, sensory receptors capturing the sensory information passed to the neurons. From an artificial intelligence perspective, this could be the camera used to capture the visual information for the robot, the wired and wireless technology used to transmit that information from the camera to an internal processor in the robot that completes the calculations, and the hardware in which that data is stored, as well as the motors and any other internal mechanisms that will allow the robot to translate that visual data into an appropriate physical response, such as picking up an item. In addition to theorizing levels of analysis, Marr developed theory for the stages of visual processing. The first stage, vision input, entails exactly what the name suggests, the reception of sensory information by the retina sensory cells. The next stage, primal sketch, involves extracting the most basic features of the image. Imagine an artist who completes a quick sketch before beginning their full detailed drawing. This sketch emphasizes light, dark, edges, and corners, the basic constructs of the larger image they're working on. Marr asserts that the third level of vision is the 2.5 dimension sketch, the 2.5D sketch, which provides additional detail, including depth, contours, and the orientation of the object in space. These two stages, the primal sketch and the 2.5D sketch, allow the individual's visual system to identify several key visual elements: the shape of the object, its placement in the visual field relative to other objects in the environment, the light reflective properties of the object, ambient lighting, depth, orientation of the individual to the object, which provides a sense of the individual's viewpoint. The final stage, the 3D model, provides the greatest details and involves prediction about the shape, contours, and volumes of the sides of the object that cannot be seen, but are based upon the relationship of the observed individual components of the object, as well as memory of similarly shaped objects. So here, we can see this side of the bowl, but we can't see the opposite side of the bowl in this image. But we can mentally infer that there is indeed an opposite side to this bowl, even though we can't see it in this picture, because our memory and experience has shown us that a bowl is a 3D, a three-dimensional object that will have a full shape, more than what we view here. So the 3D perception incorporates this fuller picture of what the 3D object actually looks like, even though from our viewpoint, we can only see this 2D flat surface. Some critiques of Mars' stages of vision include that he does not account for visual attention. Imagine that you're standing on a street corner, about to cross the street. You can see the stores surrounding you, the people inside them, the items in the windows. You can see the trees lining the sidewalk, the clouds and the sun and the sky, the people walking past you, the cars driving up and down the street. Your photoreceptors activate in response to this wide array of visual information. But if your goal is to cross the street, what would you do? You might look at the crosswalk signals to see if they indicate that it's safe for you to walk across. You might also look at the traffic light to see if it's signaling cars to stop, go, or slow down. Or if you're from New York, you glance at the cars for a quick second to see if you can jog across the street without getting hit. Regardless of which one you choose, hopefully you look at the crossing signal and the traffic light and assess the cars before you cross the street and promote safety. But regardless of which one you choose, what's the similarity among each potential action? The choice to divert your visual attention to a specific component of all the visual information before you. As you quickly glanced at the cars before jogging across the street, it's possible that you also saw the cute dog passing in your periphery, but your visual attention, despite how adorable and fluffy he was, your visual attention was not focused on that information. It was focused on the cars that you can make sure that you got safely across the street. Now, the example I've given you reflects a conscious choice to focus your visual attention on specific aspects of your surrounding environment. But this process of encoding the visual scene, selecting specific aspects of it to focus on and allocate for conscious attention, and decoding properties of that visual scene also happens unconsciously. Visual experiences, such as hemispatial neglect, lend further credence to the theory that perception, especially as it relates to vision, incorporates, as Helmholtz would say, unconscious inference. Hemispatial neglect usually occurs in individuals with damage to the right inferior parietal lobe. So that's the right side, the attention network, and can result in loss of awareness of the visual stimuli on the contralateral side of the visual field. Contralateral means the opposite side. So if the lesion is on the right side of the brain, the visual would experience contralateral hemispatial neglect, that is, loss of vision on the left side. So contralateral means the opposite side. And ipsilateral refers to the same side. This is not a visual, hemispatial neglect is not a visual deficit in the traditional sense, as evidence has shown that the visual cortices remain intact and damage-free in hemi-neglect patients, although the symptoms seem to manifest visually. Their basis neurologically isn't in the visual cortex. It's in the right posterior parietal cortex. Hemi-neglect patients perceive only half of the visual world and objects before them, although in terms of visual information passing through the retina and to the visual cortex, they have actually seen the image or object before them on both the ipsilateral, on both the side ipsilateral and contralateral to the lesion. The key insight emerging from this deficit is the knowledge that there are additional stages of processing that occur after or in conjunction with visual processing to produce perception. Consider the images beneath copying and spontaneous drawing. They reflect drawings created by an individual suffering from hemispatial neglect. This individual demonstrates lack of awareness of the left side of their visual field, both when copying visual stimuli presented to them, as well as when drawing from memory. Recall that this individual's photoreceptors, the visual sensory receptors in their eyes are functioning properly, and their visual cortex in the occipital lobe has not incurred damage. Rather, this deficit represents a perceptive deficit resulting from damage to the right inferior parietal lobe. Even more interesting is this last image on the right. So consider the drawing on the right, the one of the two houses. Notice that one is on fire and the other is not. When hemispatial neglect patients were asked to describe the two houses, they said that they both looked alike, confirming that those with hemispatial neglect were unable to perceive the left side of the house. Interestingly, when asked which house they would prefer to live in, the individuals indicated that they would prefer to live in the house on the bottom. You know, the one that's not on fire. This seems to suggest that the visual information about the state of the house on the top was processed. However, a perceptual defect prevents the individuals from seeing that difference that they have, even though they have stored that information via another modality. So even though they do not perceive that the house is on fire, when asked which one they prefer to live in, they pick the house that presents them with more safety. So it seems as though information about this house being on fire, perhaps being a danger to them, was stored in some manner. Although the individual is able to see visually that the objects before them they are only aware, perceiving half of the image. Even more fascinating, even when drawing from memory, individuals create images that neglect details on one side of the image, indicating a disconnect from perception of the whole image drawn from memory. If there is not damage to your retinal photoreceptors or ganglion cells, meaning that they are receiving and passing visual information, what is happening in the black box of perception within the brain that's preventing this individual from perceiving the full scene before them? Challenges such as hemispatial neglect lend additional support to the Helmholtz theory of unconscious inference and theories of information processing and the computational approach that suggests that the brain processing this visual data, that the brain is processing this visual data in a manner that leaves the individual unaware that these processes are taking place. Cases such as hemineglect allow us to better understand what happens normally by providing examples of the effects of lesions to various parts of the brain. Blind sight is like the reverse of hemispatial neglect and is just as fascinating, honestly, in my opinion. Individuals with blind sight have damage to their visual cortex, creating a blind spot in terms of their ability to literally see the visual information before them. So imagine when you're looking at something, one section of your view is obscured by a gray spot, a blind spot. Just for the fun of the intellectual exercise, imagine that you experience such extensive damage to your visual cortex that you were completely blind. You could not visually see any of the stimuli around you. Would you be able to, say, walk through a room filled with obstacles that you'd have to navigate around, like chairs, tables, or desks? Believe it or not, researchers have recorded such abilities in those labeled as having blind sight. In minor cases, some individuals are presented with images that appear within their blind spot, and they are asked to report on the features of this image, the direction of lines, color, that appear within the blind spot, such as color, orientation, and shape. Data has shown that these individuals report accurately responding to these questions with better than chance accuracy. I recall one article reported, I think, 80% accuracy. That's rather high, and certainly better than chance accuracy. Okay, well, maybe they got lucky, statistically unlikely, but maybe. Let's consider another example. Another patient, TN, was clinically blind. To confirm that he was clinically blind, researchers used brain imaging methods to confirm that there was no activity in his visual cortex. Then they convinced him to attempt walking down a hallway that was cluttered with obstacles, although he was not notified of this. Despite being unable to consciously see the hallway, TN flawlessly walked down the hallway, turning his body this way and that to navigate around the obstacles in his way. Just as was demonstrated in the examples of patients with hemispatial neglect, blind sight provided additional evidence in support of the theory that a process of unconscious inference, unconscious processing of visual stimuli in support of perception takes place. Despite the inability to visually see the objects before them, patients with blind sight are able to guess about the components of visual scenes before them with greater than chance accuracy, as well as navigate 3D space with obstacles around them, which they must navigate. That's pretty incredible. Get some tea. As it relates to sensation and perception, neuroscience aims to understand several components of these processes. The sensory structures that allow us to translate external physical stimuli into a format that the human body and brain can understand, as well as the neurons that receive these signals and pass that information to other neurons and neuronal circuits. Neuroscience seeks to understand the morphology of these cells, their electrochemical properties, how these properties facilitate communication, as well as how these properties allow neurons to convert physical stimuli into electrochemical signals, their behavior in isolation from other cells, as well as their behavior in conversation with other neurons and regions of the brain. While neuronal activity does not occur in a vacuum, and certainly entails communication with a vast network of other cells. Single-cell exploration has yielded valuable contributions to the human understanding of sensation and perception. Consider for a moment how the microelectrode transformed the neuroscientific landscape and our knowledge of sensory and perceptive processes. The microelectrode is a recording and electrical stimulation device so small that it is able to pierce the membrane of a single neuronal cell without rupturing it. Think of it like how your skin is pierced when you're getting a shot at the doctor's office, except on a much smaller scale and with the added benefit of being able to record electrical activity as well as deliver electrical stimulation. The ability to record activity in the cell allows researchers to present a variety of stimuli to determine what kind of stimulation excites the particular neuron being recorded. That kind of data provides information about the differing roles of different types of neuronal cells. Consider again the work of Hubel and Wiesel. They explored the sensitivity and reactivity of single neurons in the visual cortex of anesthetized cats. Their work revealed that certain neurons are insensitive to diffuse light, such as the light in the background here in my room, but are sensitive to light spots. Recall the discussion earlier in the lecture about the importance of the ability to discern edges, especially in the view of Gestaltists. In addition to researching how physical stimuli impact the activity in single cells and networks of cells, neuroscience also deepens our understanding of sensation and perception via neuropsychology. Neuropsychology is the exploration of how differential states in the brain impact behavior. Differential brain states can be brain damage, such as caused by a stroke or a lesion. The activity in certain regions of the brain can also be manipulated using experimental devices that inhibit or excite brain activity in certain gross regions, such as via transcranial magnetic stimulation, or TMS. Application of TMS, a neuromodulatory technique, involves the application of a magnetic field to the scalp using a device, which induces an electrical response in the brain's neurons such that the activity can either be elicited or inhibited. Inhibition of neural activity presents the opportunity to explore the effects of this functional lesion. That said, neuropsychology allows researchers to explore the relation of actual brain damage, functional brain damage, and altered brain states on behavior. Brain lesion, functional lesion, and altered states provide opportunities for scientists to explore the impact of these changes. Cessation of activity in a region of the brain, for instance, on the neurotypical processing of sensory information, memory, language, emotion, and decision-making. Consider the case of DB, described in the chapter. He had a malignant tumor that doctors determined it was necessary to remove. As the tumor was causing seizures, it might have become life-threatening if it were to spread to other regions of the brain or body. Although the surgeons worked carefully to remove the tumor and only the tumorous tissue, they ended up excising a large amount of brain tumor from the visual cortex located in the occipital lobe. The surgery was a success in that it allowed DB to return to work and live a life with fewer, if any, seizures and no concerns about the tumor spreading from its current state. However, it did come at a cost: the development of a scotoma, a partial blind spot in the visual field, due to damage in the visual cortex at the back of the brain. Of particular interest to neuropsychologists studying perception might be the study of agnosias, a deficit in some aspect of perception as a result of brain damage. For example, damage to the fusiform face area of the temporal lobe might lead to prosopagnosia. This is a deficit in an individual's ability to recognize faces. Imagine that. If you had damage to your fusiform face area, you might not recognize your family members' faces. Whereas damage to the right temporal lobe might result in amusia, an individual losing a sense of appreciation for music. For me in particular, that would be tragic. I love music. So, we can explore neural activity and its role in sensation and perception at the single cell level with microelectrodes. We can explore the impact of lesioned, impaired, and functionally impaired regions of the brain of sensation and perception by observing the behavioral changes. But what if, as scientists, we're interested in exploring the activity and role of certain regions of the brain in neurotypical or healthy patients? And what if we want to be able to visualize structural abnormalities and functional communication between regions? Magnetic resonance imaging and functional magnetic resonance imaging are great tools for these kind of queries. So, what is magnetic resonance imaging, or MRI? Let's do a deep dive. MRI is a neuroimaging strategy that allows scientists to visualize the structures of the brain. And in functional MRI to visualize the regions of the brain that are active during certain experimental conditions. So, how does MRI work? To understand how MRI works, we have to recall a few biology and physics facts. Recall that the body is over 60% water, and that the hydrogen atoms in those water molecules, H2O, H stands for hydrogen, are sensitive to magnetic fields. The MRI machine itself has, so there's that. The MRI machine itself has several crucial components. An incredibly strong magnet inside the MRI machine that creates a unified magnetic field around the individual inside the scanner. A gradient that adjusts the magnetic field into sections so that different strengths are applied to different parts of the body, allowing research to isolate activity in that region. Normally, when you're walking around, not inside an MRI machine, the water molecules inside your body are arranged in a random order, just spinning around willy-nilly. But the application of the magnetic field causes most of those water molecules, the hydrogen, to move or align in a uniform manner, leaving just a few non-conforming rebel water molecules spinning in their own unique way. Here's where the radio waves come into play. While inside the scanner, essentially this giant magnet, the MRI machine also applies radio waves that resonate with the magnetic fields of those non-conforming rebel water molecules and forces them to align, just like the other molecules. When this radio wave is stopped, the non-conforming rebel water molecules return to what they were doing before. So think of the magnet like having a teacher in the classroom full of kids. Most of the kids will quiet down and pay attention, but a few rebels in the back are still chatting and throwing spitballs if you're old like me. The radio waves are like the teacher calling the principal into the classroom. When the principal arrives, even the rebels in the back straighten up and pay attention. That is, until the principal leaves the classroom. Then it's back to chatting and spitballs all over again. So how on earth does this translate into a brain scan? When the MRI machine turns the radio waves off, when the principal leaves the classroom, just like you can see the change in the student's behavior, you can measure the change in the activity of those rebel water molecules. This change in the non-conforming water molecules is sent to a computer that translates this data into images of the body or the organ being imaged. But how do you get a 3D image? So imagine that you had a potato. I know I'm using a ton of metaphors here, but imagine you had a potato and you wanted circular slices. You put the potato on its side, and then you just cut from one end to the other. And you'd have a handful of slices, and if you held all those slices together in order, they'd have the shape of the potato before you cut it up. The machine repeats this process of targeting radio waves at certain parts of the body over and over again in slices for the region that it's targeting. After it does this, for each slice of the brain, the computer combines those slices in the proper order to create a 3D image. So you've got slices from the chin to the top of the head, you've got slices from ear to ear. And you can even do slices at angles. It depends on the type of scan that you select. But how does the scanner tell the different parts of the brain apart? Different regions of the brain have different amounts of water. Differences in the amount of water or hydrogen atoms allow the MRI to discern the different parts of the body. So that's the structural portion of the MRI scan that allows us to see the anatomy of the brain. So just imagine these color blobs aren't here yet. That's the functional part that I'll describe next. So how does the MRI allow us to see what regions of the brain are functioning, these red spots here, or active during certain experimental conditions? This is measured using the hemodynamic response. I know, more biology, more stuff, but I'm gonna make it super clear. This is measured by the hemodynamic response, which is the delivery of blood to areas of the brain that are more active. So fMRI is actually an indirect measure of neural activity. So how does the fMRI measure a hemodynamic response? Oxygenated versus deoxygenated blood, so blood with oxygen in it or blood without oxygen in it, have different magnetic properties. When the hemoglobin in our blood is not carrying oxygen, it is more sensitive, that means more magnetic than when it is carrying oxygen. fMRI takes advantage of these properties, and as it can detect the difference in magnetic sensitivity of these oxygenated versus deoxygenated blood, thus allowing a collection of data that shows regions of the brain rich in oxygenated blood or deoxygenated blood. The assumption is that regions with more oxygenated blood and thus less magnetic are more active than those regions with less oxygenated blood. So more oxygenated blood, more active regions, less oxygenated blood, less active regions, and the level of oxygen in those tissues allows the MRI scanner to tell those different parts of the brain apart. The measurement of blood oxygenation level is called the blood oxygen level dependent signal, or BOLD. The observed tendency, the BOLD signal. The observed tendency of the body to send increased amounts of oxygenated blood to regions of the brain that are more active, such as those engaged in a sensory or perception task, have allowed scientists to visualize the brain's response to certain tasks, such as listening to music or following a visual cue. While both MRI and fMRI are incredible diagnostic and research tools, MRI does have limitations. For example, while the MRI provides great spatial resolution, allowing us to see single-digit millimeter level accuracy, its temporal resolution doesn't get much faster than a couple of seconds. For contrast, other measures can provide millisecond level measurements of activity. Furthermore, even with this excellent spatial resolution of single-digit millimeter accuracy, we're still looking at the activity of vast groupings of neuronal cells. And finally, our last slide for today's lecture, just so that you know the end is near. Can cognitive and emotional states affect the phenomenon of perception? An interesting question. Cognitive penetration is the term used to describe how different cognitive and emotional states can influence the phenomenology of perception. Conversely, cognitive impenetrability suggests the opposite, that perception does not vary due to different cognitive and emotional states. Instead, this concept asserts that what changes is not perception, but instead attention, expectation, and mood. From this view, the change in attention and mood states influences the phenomenological experience of perception rather than altering perception itself. While cognitive impenetrability is the dominant perspective, that is, perception does not change in response to differing cognitive and emotional states, some research indicates evidence in support of cognitive penetration. For example, Delk and Fillenbaum conducted an experiment exploring cognitive penetrability using color. They asked participants to match the colors of different objects, which all had a red-orange color hue, with the background's color so that they'd match. Some of the objects, such as an apple or a heart, were associated with certain colors, such as red. In this experiment, participants added more red to the background color of the objects that were associated with the color red, such as the apple and the symbolic heart. This evidence was interpreted to suggest that particular knowledge of the real-life color of the object was influencing their perception of whether or not the background color that they were adjusting was sufficiently red. Similar evidence of cognitive penetration was found in other studies, exploring the impacts of pain-relieving creams on perception of pain. Individuals were given a cream that they were told would increase their pain, decrease their pain, or be neutral and just keep it the same, or not do anything, not influence it in any manner. Although the three groups were each given identical creams, the group that was told the cream would increase pain reported greater pain relative to the control. And the group that was told that the cream would decrease pain reported less pain relative to the control. These visual irregularities or biases as a ride happen with everyday tasks such as driving. Dr. Patricia DeLucia has dedicated time to studying perceptual differences related to collisions. Evidence has shown that people will estimate that large objects such as trucks will collide with them sooner than smaller objects such as bikes and motorcycles. DeLuca attributes this difference to two cues: time to collision and size arrival effect. Time collision refers to the process by which our visual systems determine when an object will collide with us as a function of the object's size at a given time and its rate of expansion in our visual field. Imagine a truck approaching you at a very slow pace. It will appear to get larger as it gets closer to you at a slow pace. Now imagine that same truck barreling towards you. It'll appear to get larger, this time at a much faster pace. This is the concept of time of collision. Size arrival effect, on the other hand, refers to the concept that larger objects are perceived to be closer than smaller objects, which leads to the illusion that smaller objects, like motorcycles or bikes in comparison to trucks, are less likely to collide with you as you change lanes or turn, for instance. These perceptual biases are considered to potentially contribute to high instances of drivers colliding with motorcyclists or bicyclists. So that concludes lecture 1 of our sensation and perception class, exploring some of the details of what is perception. Feel free to reach out to me via email if you have any questions, and I'll post the discussion questions. The discussion questions are probably posted already, and you'll have a quiz due at the end of the week. Once again, please do feel free to email me if you've got any questions, and we can also schedule a time to meet during my office hours. Take care, y'all.